So we know that ideal gases don't really care what they're bumping up next to. So this leads us to this understanding of Dalton's law of partial pressures. So basically, super difficult here. The total pressure of a mixture of gases is equal to the sum of the pressures of the individual gases. Okay? Now, if you go further into chemistry, there's obviously some other things that go on here, but the basic understanding here for Dalton's law of partial pressures is basically total pressure is just the sum of the individual pressures. So here I've got some helium at 2 atmospheres, some argon at 4 atmospheres. If I mix the two of them together, 2 atmospheres plus 4 atmospheres gives me 6 atmospheres. Here I have random gas A and random gas B. One's at 300 millimeters of mercury, the other's at 400 millimeters of mercury. If I mix them together, now my gas mixture has 700 millimeters of mercury. Okay, so here's a really complicated example problem for you. Venus, we have these 3 gases at these 3 pressures. So what would our atmospheric pressure be? We're going to take our 300 and if I can get my Apple Pencil to cooperate, we're going to take a 392 torr plus our 834 torr plus our 302 torr, and we're going to get 1,528 torr. That's it. That's how we calculate that. Now, one of the things with Dalton's law of partial pressure, though, is it lets us do some fun things. So one thing is it lets us understand some stuff going on with vapor pressure. So our vapor pressure is the pressure that's exerted by a vapor in equilibrium with its liquid. Okay, so it's whatever's vaporized on top. So let's say I collect some gas over water. Well, I can set my apparatus up such that I have a situation where I can make my own sort of manometer. And if I do a pressure equalization, then my atmospheric pressure will be equal to the partial pressures of my water vapor over the water and my gas. Now, if I take the temperature of my water, I can get the vapor pressure of my water because water is super well known. I can look that up in something like the CRC and be, at X temperature, the vapor pressure of my water is Y torr or Y atmospheres. And if I know the atmospheric pressure, and I know the pressure of my water vapor, I can get the pressure of my gas. Okay, and so it involves an equalization step, but it's really cool. So it lets us make some calculations when we collect gas over water. When we talk about boiling point, we're just looking at the temperature where the vapor pressure equals that external pressure. And so our boiling point depends on applied pressure. And so this is why if you are cooking at different altitudes, sometimes the directions are different because at sea level, we have higher external pressure. We need more energy to form bubbles, which means it boils at a higher temperature. At higher elevations, okay, we have less external pressure because our atmospheric pressure is lower. And so we don't have to get as much energy to enter the vapor phase. And so it's going to boil at a lower temperature. When my aunt moved from San Diego up to this small mountain town near Yosemite, she moved to very high elevation. And she had to follow high elevation cooking guidelines on like boxes of mixes and stuff and get used to cooking at high elevation because things boiled at a slightly different temperature. And so some things would take longer to cook because if water's boiling at a lower temperature, you're not going to get the same amount of heat. And if you don't have the same amount of heat, if you have a lower amount of heat, you have to cook it for a longer amount of time. And she said it took a long time for her to get used to that when they first moved up there. So, implications of what happens with these gases.